Welcome to a lesson with Dr. Powell. Let's take a look at this matrix multiplication as the result of a bilinear transformation. What does it mean to be a bilinear transformation? That means there's two vector inputs. Look, there's a column vector input and a row vector input. And, if we let everything here be constant and let the column vector vary, that's a linear transformation, right? Because that's like a matrix times an input vector, that's linear. And if we let this be constant over here and let this be the input as a row vector, that's a linear transformation as well. That makes it bilinear. If we let one entry be constant into the function and one input be constant, one input vector be constant, then it makes a linear transformation out of the one that's variable and vice versa. So it's bilinear. All right. So we could go ahead and just matrix multiply it to evaluate it, but there's something kind of neat about this bilinear transformation here, written as a matrix. See this 2 right here? That's actually the result of what you'd get if you plugged in 1 0 0 and a 1 0 here. You would end up getting 2 out of that. Similarly, if let's kind of think, okay, this is like think of this as a row, like row positions. This is like first row. Okay, so this means right here, first column. So first row, first column is 2. Likewise, if we put in let's see, how would we get a -1 out of that? Well, we would need the second row, and we'd need the um, second column. So we'd have 0, 1 here. And that would end up getting us that -1 as desired. So in the matrix itself are kind of like the outputs of all of these pairings of standard basis vectors as we go through. That mechanism allows us to do the following to compute to do this matrix product. What we could do is we could think of this as an array of numbers, 2, 0, 1, -1, just taking the matrix, and then multiply the top row by 2. Okay, so um, multiplying the top row by 2, sorry, we get a 4. Why am I doing that? Because I'm looking at this 2 right here. Okay, now I multiply the next row by 1, it just stays the same. Multiply the next row by 0, just zeros. Okay, now for columns, I multiply the first column by 1 and the second column by 1. Great. So then I just add up these numbers. Let's see, right. So the columns 1, 1, and we had 2 times that. And yeah, that looks good. So when I add these up, I end up getting just 4 as the output. Now, you could matrix multiply this any way you want and see that you actually do get 4 as well. See what I did? What I did is I just took this matrix and I said like 2 times that row, 1 times that row, 0 times that row, then 1 times that column, 1 times that column. And then I saw this in this array of numbers. I just add those up and I get the output. Let's see if that actually works here when we matrix multiply it. So in a column interpretation, if I have a 1, 1 here, that just simply means add these 2 columns together. So 2, 0, 2. Then this 2, 1, 0 just simply means 2 times that, 1 times that, and 0 times that, and add the results. So that ends up being 4, as desired. Boom, done. This is just an alternate way of thinking about this matrix product as a bilinear transformation. And part of that is this idea of a tensor product. Kind of what we're doing here is we're thinking about um, this. Okay, so what we're doing is we're thinking about this. We're thinking about looking at pairings of things. So here we have like an E1 basis vector. It's a row vector, an E2 and an E3. Over here we have like an E1 and an E2. We could give these different names if we want to, like maybe R's and C's, so we can kind of keep track of where they're coming from. So like a row 1, row 2, row 3, and then column 1, column 2. And the entries in the matrix themselves right here are representative of like the outputs of different pairings between these guys. How do we represent pairings between things over here and things over here? We do that using the idea of, well, we use this symbol, but basically it's just like a comma. It's like pairing something from this input with that input. So kind of we have like R1, C1. So what we're doing is we're specifying, we're changing the domain of our bilinear transformation to a vector space. Instead of a tuple of vector spaces, we're having a vector space of tuples. Okay. So we can kind of, and our bilinear function just becomes a function from things like this. What would this be? This is kind of like inputting a 1, 0, 0 in here for the row, and over here inputting like a 1, 0. So plugging that in and seeing what you get out. And we know that would be just be 2. So if we had a vector space where the bases were just guys like this, we know exactly what the output of each basis vector is, and we have a very nice, and this mechanism has allowed us to change our bilinear transformation actually into a single linear transformation if by just changing the domain into where the vectors are just tuples of vectors, but we use this symbol. Now, and behind the scenes of what I just did was actually that very idea. What we can do here is we can kind of think of this as being, let's see, the input over here is like 2R1 plus, so 2R1 plus 1R2. And the input coming from here was like 1C1 plus 1C2, or just C1 plus C2, right? But okay, and our bilinear transformation is a function, just call it like F. And what we can do is, instead of using this comma, we could think of it as we could think of our domain as being tuples, and now it's a linear function. And and all the bilinearity comes out in how this works. This works just like multiplication. That's why we put this, and how it pairs things together. The pairing kind of distributes across each other, and the two as we go. So think of just a FOIL. So think of like 2R1 paired with C1. That's like first. Outside would be plus 2R1 C2. Inside would be plus R2 C1. And then last would be plus R2 C2. So we have a function, a linear function with all this coming in. Now what can come out? See, this 2 can come out of this. So the linear function splits across the addition, and scalars come out. So we can kind of think 2f of R1 tensor C1 plus 2f of R1 tensor C2 plus f of R2 tensor C1 plus f of R2 tensor C2. And then, you know what, now this is just the image of that place right there, right, which is in the matrix, just a 2. So this is just 2 times 2 right here. That's 4. This is R1 C2. Let's see. So row 1 C2, that's a 0. That's just a 0 times, that's a 0. This R2 C1, let's think that's row 2 and 1. That's a 1. Just a 1 right there. And this guy right here, this is row 2 C2. It's a negative. So it's a negative 1. And so we end up getting 4, 1, negative 1. Now notice we saw this earlier. If you rewind the video, we saw something like this and then we added the entries. That's exactly what happened right here. Um, so this was, so the mechanism of why this worked was due to this pairing idea and how it works with multilinear functions, bilinear functions in this case, because there's two entries. If I had like because there's like two vector entries. If I had another one, I'd have to describe this matrix in another way, perhaps see there's like a row interpretation and a column. I'd have to have like a stacking interpretation, like with levels, and have another vector input over there. But all this can be described, if we want, by these guys. And that allows us to maybe not have these bizarre stacking and other things in multiple dimensions, in higher dimensions. So that's what that is. Okay, well, this was a little description of bilinear functions and how they relate to the tensor product, and how we can, and even just how a regular matrix can be thought of as a bilinear transformation if you think about a column input and a row input coming into it. Thanks for watching.